Ja, ein neuer Versuch, diesmal ohne Bild, damit wir es noch hinbekommen. Oh, sorry. But we need now our t-values and we need our f-value, and the t-value, this is t beta, is just beta over the standard error of beta. So let's go in here, and there we have the betas, and then, so to speak, the T0, T1, and T2 is then just our parameters beta, and there are our betas, 0.4, divided by our standard error. And I should resize this again, or yeah, okay. So then let's copy this also down here. So these values are now t-distributed. So these are, oops, t-distributed, and we need the f value, and the f value was r squared divided, hopefully I'm right, by k over 1 minus r squared by n minus k plus 1. But this I do not have in my head, so I just look it up. I'm back in a second. Where did we have the f value? This is here. So r squared over k n minus k plus 1. This is also okay. So, and this then we have to calculate. Let's go here. This means f is r squared. We have r squared here over k. This was 2. Large line. All this divided by 1 minus r squared over n 7 minus k is 2 plus 1. Closing brackets. Oops, there is, I think, one bracket was missing. Well, and if you look at this number here, and we are going up here to the right again, also this number is directly calculated for us. So this is then 104.84. And this is then 0.98 over 2, 1 minus 0.98 over 7 minus 2 plus 1. And here we have this one. So I'm now running out of space. Therefore, what do we need? We need now the t values and we need the f values. And the rest we don't need anymore. So again, these are t distributed. So what we want to do now is we have this significance level of 5%. The t distribution is symmetrically almost a normal distribution, and therefore we have now to look up the theoretical critical values such that this mass here and this mass here, how much probability mass we have to have in the two tails if the significant level should be 5%. Yeah. Not 90 inside, 95 inside, because this is then the probability where, so significance level of 5% means we do not want to reject H0, that our betas are all 0, if we are within these interval here. So within this here, then is 95 if we have a significance level of 5, and the other one, then the two tails, since it is symmetric, this has to be 2.5 and this has to be 2.5%. So, and with this, we can go into our t-distribution table. And where we are, I think this was too fast. No. Yeah, where we are. T. Here we are. So n is 7 minus k plus 1. So we have to look at 4. And since the critical point is then on the right, 97.5, because the left part is only 97.5, then we have to look at this number here. Up. So this one. Let's cut this and this for the t distribution. So here, this 4, this is 7 minus 2 plus 1, and 9075, since at this point all on the left the probability mass is 97.5%, because then of course we have to add this here too. So this would be then our critical value. So we have 2.77 minus 2.77, and then we compare this for T0. We have, sorry, not there. We have here T0 is 0.84. T2 is 0.53, and T1 is somewhere here, 3.61. So this means H0 is not rejected for beta 0 and beta 2, alpha equals 5%, So these two parameters do not significantly differ from 0 for alpha, of course, equals 5%. Well, and this is a really important result, because if we make only the descriptive analysis, then more or less we find, okay, we have a very high correlation. We have this coefficient of determination of 0.98. Well, I'm starting to rely on my model. And now the statistical analysis shows me that two of the three parameters do not really statistically differ from 0 from my data set for a level of 5%. Well, and then let's do also the F-test. This then means we look at the F distribution, and there 10%, so F theoretically would then mean all this here should be 90%, since we want to have a level of 10%. And this, now we have to see what is this theoretical value compared to our empirical value of 104. Okay, so then let's go into our F distribution. I think it was the last one. Yep. 95, 99, 90, 75. Hopefully I have the 90 also here. So we need the 90% table, and we have our two parameters, k and n minus 2 minus n minus brackets open 2 plus 1. So 4 and 2 are my parameters. So we need up to this, let's say, and then we have this point here, 2 and 4, and we are at 9.32. So this is then 9.29, and we are somewhere here on the right with F empirically equals 104. So for alpha equals 10%, the assumption that at least one beta is differing from 0, or this is the same statistical issue, or R squared is different from 0 is no, I have to formulate it the other way around, sorry. The assumption that all beta are differing from 0 or r squared is equal to 0 is rejected. So from this point of view, qualitatively speaking, it is okay that we make a linear regression. And this result that we are here quite on the right side, this is also not that surprising, because let's go to the F table. If we take also the same significance level 5, then you see here we would have to choose 19, so 20. Then we have the same significance level in the t-test and the f-test. And we have seen within the f-test for 2 parameters, they are not statistically fluctuating to a level of 5% from 0, but there is one parameter here, beta 1, which is quite far away for a significance level of 5% not to differ from 0. So this is then also a possibility to double check your calculation. So making the f-test and making the beta, the t-test, and they should more or less correspond. Well, of course, these are statistical issues. It could still be possible that, on a qualitative way, you have a question mark. Why do they more or less contradict? But in this case, we see this is very, very improbable that if we have here, there one parameter is highly significant not to be 0 from the t-test, that in this case we would have the result from the f-test that r squared is not differing from 0. And let me take 2 minutes, please, because here, if we calculate just the correlation between x1 and y and x2, this just in a minute as you see this, so r squared x1 y and r squared x2y. So what does this mean? Then we just would say, well, we have only one x and one y, what we have done in the simple regression. And if we calculate this, then we have to feed in just our y values and the x1, and here the y values and the x2 values. So, and what we see here is, well, both x values are highly correlated with our revenue. So from a descriptive point of view, we would say, well, both variables are very important to determine our revenue in our stores, because we have here 98 and 92%, more or less explaining our why. But of course, what we also have is that r squared x1 x2, if we calculate this one, then we have also a very high correlation between these two variables. And well, what does this mean? We have two variables which have very high correlation with our output variable. Then we are maybe quite happy. But these two variables have also itself a very high correlation to itself. So what we are then here more or less doing in our analysis is we have two variables where we assume that they are independent, which are highly dependent to each other. And this then would mean that we overspecified our model. So we feed in additional data. There, in general, we say the more data we have, the better it is. But here, it seems to be useless to use a second variable. And the analysis which we have done then means more or less that, yeah, the variable x2 is maybe the more important variable in order to explain our revenue, and that we have really to be careful also to add the information from the size of our stores within our model. And I don't know if somebody of you have this topic. One topic in the term papers was misspecifying a model. You have it? And this is, so to speak, a simple example where you are doing all this, and maybe if at first time you say, well, great, I have a great explanation of my revenue in my in my data, and then but you see then that you have to be really careful that you do not interpret it in a wrong way afterwards. Okay, so thank you very much for today, and